Hello, guys. Sorry, fly in my face. So I want to spend some time with you now, helping you prepare for your rocks and minerals test. And I wanted to go over the review with you really well. So we're going to do that together today. And I don't say this to scare you, just so that you know that you need to prepare. This is a big assessment at the end of the unit, and it is not eligible for a retake. So just keep that in mind. And use your review sheet in this video to really help you. So in our study of rocks and minerals, we started, of course, with minerals. And the four traits of minerals are that they have to be solid, non-living, natural, and made of crystals. And so our second question asks what minerals are the building blocks of. And of course, they are building blocks of rocks. So when you guys look at this picture with me, you notice how you see different colors and shapes of crystals in this rock. Those are all different mineral ingredients, or we can say different mineral building blocks. Now, we did need to get into a little bit of chemistry because of the way minerals are classified. And so there's a little chart there for question 3, that there are 3 small parts of the atom: protons, neutrons, and electrons. Most students do a very good job of remembering that protons are positive. However, a lot of times this is mixed up. Neutrons are not negative. Neutrons are neutral. Think no charge, neutral neutrons, and negative electrons. And so when we look at how an atom might be diagrammed, right? So the positive protons in the center, which is called the nucleus of the atom, and then the negative electrons swirling about the outside. So think to yourself, what does that leave those green things to be if the positives are protons and the negatives are electrons? And of course, those would be the neutral neutrons, also hanging out in the nucleus of an atom. Okay, so we worked on the idea that minerals can either be elements or compounds. And so here's an example of a mineral that is an element. The answer to number 4 is element. This is a picture of a lot of gold. And so if we could see the atoms in the mineral gold, they would all be identical gold atoms. You wouldn't have any other types of atoms, and that's what makes it an element. Now check out this mineral. This is the mineral galena, and it is actually a compound, which is the answer to number 5. Here's the reason it's a compound. It is not made of one type of atom, it's made of 2. This is a compound of lead and sulfur. So if we could actually see the atoms in galena, in this mineral, there would be 2 different types within it. So the reason that we did all of this actually has to do with how minerals are classified. The answer to number 6 is chemicals. Minerals are classified by their chemistry into these 2 groups that you should remember from the past, called silicates and non-silicates. And so when we think of the chemistry of a mineral, there are actually some chemical possibilities. One of them, and this is getting to question 8, one of them is that a mineral could have silicone in it but no oxygen. Another possibility is it could have oxygen but no silicone. And the one that we sometimes don't think about is it could have neither. Like gold is an example of that. Gold is just made of gold atoms. It doesn't have any silicone or oxygen. And of course, it could have both silicone and oxygen. So the only right answer to number 8 is D. That is the recipe to have a silicate mineral. So on your test that's coming up, there's going to be a graph that shows all the different minerals within a rock. And to determine if it's a silicate or non-silicate, you're looking at for 2 bars on that graph. Finish my thought in your own head. Does it have silicone? And does it also have oxygen? And if you can say yes to that on the graph, it's a silicate. If you don't see both, it's a non-silicate. So then we got into some mineral identification. So we actually classify minerals into silicates and non-silicates by their chemistry, but we identify minerals by their properties. It's really no different than how we identify each other as we look at our properties or our traits. And so we are going to work first to define the properties, and then I have some good pictures to help you remember. So color is just what it sounds like, the color on the outside, and it's actually not super reliable due to weathering. You probably remember that. So sometimes the outside color can change. Streak, on the other hand, is the inside color, and it is more reliable. Let me show you that picture real quick, and I'll come back to the next answers. So this is showing you how to streak these minerals, and you can see here that the streak and the outside color really do match. So in this case, weathering hasn't messed up the outside color. So streak, we rub that on the streak plate, and it shows us the inside color. Luster is the way that a mineral will reflect light. And so when I say it's the way it will reflect light, remember sometimes it's a glassy luster, sometimes it's waxy luster, metallic luster if it reflects like a metal. Now, hardness, you might remember doing this, right? The scratch test for hardness. And so if a mineral is hard, it will resist scratching. If it's soft on Mohs hardness scale, it will scratch easily. Even sometimes with your fingernails, the softest minerals do. Now, the last thing here are special properties. And here's the deal. Whoops, excuse me, I was trying to move me. There we go. Some minerals have special properties, not all. And so it actually makes them easier to identify if the mineral has a special property. For example, halite is also known as rock salt. I'm not recommending licking minerals in the environment of COVID, especially, but it tastes like salt because it is salt. That's what's ground up in our salt shakers. Now, my favorite might be this next one. Some minerals will glow under an ultraviolet light. You probably remember seeing that in class. But here's an example under an or a couple of 8 examples under an ultraviolet light. They will absorb that energy, and the electrons go to a higher energy level. And then after that, they give off energy in the form of these colors. And you have to think: do all minerals do this? No, but some. And the final one here is a chemical reaction. So not all minerals do this, but some do. And here's a great example. So I know it's a little tough to see, but this is the mineral calcite, and it's in a cup of vinegar, which is an acid. And so can you see the little bubbles coming off of that? That's a chemical reaction. Most minerals in vinegar or in any acid, like lemon juice, for example, will not do that, but some do. Okay, so that ended our study of minerals. And what we're going to move to now is reviewing how minerals get mixed up in the rock cycle. So it is honestly so important that you understand how all 3 rock types form. And so if you check this out with me, we have, sorry about that again. There we go. So we have igneous rocks all coming from cooled magma, and that's simple. Like you can say it like that on your test. Sedimentary rocks, though, those are different. Sedimentary rocks form in you have to think of 2 processes. First of all, erosion makes the chunks. So you might have said erosion makes sediment. That's good. Sediment's just the fancier word for chunks. Now, the chunks, though, we wouldn't call sand, silt, and clay. We wouldn't call those things sedimentary rocks. So they actually have to get cemented together, or you could say smushed into layers. That happens at the bottoms of lakes and oceans. Okay, now, metamorphic rocks have their own story, of course. Meta means change and morph means form. So metamorphic rocks change form by heat and pressure. And this is not enough heat to totally melt the rock. Remember, the rock is melted, you're on a path to igneous. So now, you might think that these questions were a little repetitive, but I asked, how can an igneous become metamorphic? Now, here's the thing. In our song, it went like this: igneous rocks to sedimentary rocks to metamorphic. So I'm asking you in the next question, the second question in the rock cycle section, how can an igneous rock become metamorphic? It's like saying, how can an igneous rock totally skip over the sedimentary part? And look at the answer. It's the same as what you really just had. It doesn't matter what you start with. If a rock gets buried deeply enough that it is under heat and pressure to kind of cook the rock and change the form, it's going to be metamorphic. Now, the craziest question here is, how can one sedimentary become a different type of sedimentary? Well, it's no different than saying how an igneous becomes sedimentary, like the song. Erosion makes chunks, and the chunks get smushed or cemented, right? It doesn't matter what you start with. It matters that you have the right mix of conditions. Okay, now, next questions have to do with the crayon. So check out these pictures. So here we have someone shaving the crayon, then smushing those little shavings. Then this one is the partial melt and cool, and then the total melt and cool. So what were those 4 pictures representing? Okay, so here are the answers to questions 4 through 7, and then I'll go back and teach on it a little more. So 4 is erosion, 5 is cementation, which is fancy for smushing into layers. If you had that, that's okay. Number 6, I was trying to show metamorphic rocks, and then 7, igneous rock formation. So let's go back. So when you had the knife and you were shaving the crayons, you were acting like the wind and water, those forces to make sediments. Okay, so that was erosion, which I think is a perfect comparison. When you were actually taking those shavings and pushing down with your thumbs, that is like cementation, cementing at the bottom of oceans. Remember, erosion happens on land, the chunks get to a river. Finish my thought in your head. Rivers go to the oceans or sometimes lakes, and those sediments get buried, 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 and eventually cemented over time. So, really, at this point, we were making sedimentary rocks. Now, this is the one that I don't think is perfect, right? So, let's really think about how this is metamorphic. The whole cup is not. So, right here, where it's totally melted, that isn't metamorphic. That's igneous. Way over here, far from the heat, that's still sedimentary. So where are the metamorphic rocks in this little cup? Right here. Okay, so they're not melted, but they're close enough to this magma pocket that there would be heat and pressure, and this is how it really works underground, in order to change their form. So right here is metamorphism or metamorphic rock formation. Igneous down here, sedimentary up here, metamorphic on the border. And then finally, this one is a perfect comparison. When we do a total melt and then cool into crystals, this is showing how igneous rocks cool and crystallize. And then to end our review, we have a little bit on rock classification and then of course the big rock cycle diagram. So here's question number 1 under rock classification. We know that igneous rocks have different size crystals because they cool at different rates. I want you to think about the spoon there. And when I say think about the spoon, remember I did the experiment where I cooled the spoon at room temperature and then I cooled a spoon over ice and we saw different results. So remember that the way that we classify igneous rocks, they all form from magma cooling, but then there are 2 branches, intrusive and extrusive. Well, let me show you, well, I should do this first. The intrusive cool inside the earth slowly, so they have large crystals. And then the next one here, extrusive rocks cool on Earth's surface. Think of extrusive exit through a volcano. They cool quickly and have small chunks. So check out this picture, or set of pictures, I should say. So this is an intrusive igneous rock. I believe that is granite. And so do you notice this is showing under a microscope how big the crystals are? That white blob is all one crystal. This to me looks like basalt. And you notice that under a microscope, the crystals are way, way smaller. So this is a volcanic igneous rock that exited through a volcano, cooled quickly, because even Hawaii feels cold magma, and then had not enough time to develop big crystals. The opposite's here. This intrusive igneous rock cooled inside the earth. There was plenty of time for big crystals to develop. Okay, now let's get to sedimentary classification. So we have rocks, igneous, sedimentary, metamorphic. Igneous, intrusive, extrusive. So what's the deal then with sedimentary? It's all classified by the size of their chunks. So for sedimentary, we have fine grained and coarse grained. And so fine grained means small chunks, coarse grained means big. So study this with me. So here, this is the sedimentary rock conglomerate. It is very obviously coarse grained. You can see pebbles in it. Now, this shale, you really don't even notice sediments with your eyes. When you rub shale on the side, you can feel clay. Remember feeling that sediment in between our fingers, very powdery? You can feel the sediments. This is fine grained, and sandstone is technically a medium grained, but we really are focusing on coarse versus fine grained. And then finally, in rock classification, what is the deal with metamorphic rocks? How are they classified? So igneous, we have intrusive, extrusive. Sedimentary, we have fine and coarse grain. Metamorphic rocks, it's about the force that is dominant in the metamorphism, whether it's heat or pressure. So regional metamorphism is dominated by pressure. Contact metamorphism is dominated by heat. Now, a lot of students mix that up because I think we think contact pressure. You have to think of it like this. If heat is the dominant force to change the rock's form, it's because that rock is in close contact to a magma pocket. So this is contact metamorphism. If it's regional metamorphism, I want you to think pressure in the region. Okay, so contact metamorphism in close contact to a heat source like a magma pocket, and then regional is pressure in the region. So let me show you this. Okay, so these are 4 metamorphic rocks. You actually pronounce this gneiss. I know that's weird. You know how like gnat starts with a G? It's kind of the same thing. Gneiss and slate. You notice the layering? It's a little harder to see on the slate. That tells you that pressure was dominant. So those two are regional metamorphic rocks. Now, marble and quartzite, we do not see a layering here. That tells you that heat was dominant and that that's contact metamorphic rocks. Okay, now, one thing you're going to do on your test, you're going to see pictures of 3 different rocks. And Mrs. Shields and I purposely picked 3 that were classic examples. There aren't nothing too tricky. So what do you look for? Igneous rocks, you're looking for crystals that are not layered because there's no pressure involved in igneous rock formation. Sedimentary rocks, you're looking for little chunks. We're not gonna show you a picture that you need to feel the sediments. You're gonna see obvious chunks of rock. And usually those are layered. And then metamorphic rocks usually have layers if pressure dominates, if it's a regional metamorphism. But you also tend to see crystal formations because of the heat that's involved. So those are your look fors. Let's study these, okay? So you should be looking and thinking, which is which? And these aren't going to be the exact pictures on your test, but they're similar. So this is our igneous. You notice how you have polka dots, those are the crystals, but they're random. They're not in any layered pattern. Now this one here is metamorphic. But wait, here comes the heat. Now you have some pressure. You see how you have layers, kind of, right? But it's not like continuous perfect layers. And you notice the shininess still crystally from the heat of metamorphism. And down here, you notice layering, but the layers are continuous. You remember our sedimentary cups where we put sand, silt, and clay and let it sink to the bottom of the cup, the ocean, and we saw good, perfect layers, our soil cups too. That's sedimentary. Now, if you could feel that one, that's sandstone. You would actually feel the texture too. Okay, so those are 3 examples like what you're going to have on your test. And then to end, on the back of your review sheet, of course, we have this rock cycle diagram. And so I also wanted you to define these words. You do not have to like write out definitions, but you do need to be able to match them in a multiple choice setting. And so let's look at igneous rocks. They're eroded by the wind and water. So erosion is the process of making chunks. Then sediments are the chunks. Cementation is how those chunks get smushed to be a sedimentary rock. Now, metamorphism is changing form by heat and pressure. And then, of course, to get back up to igneous, you've got to have magma. So a metamorphic rock melts, turns into magma, and then cools into crystals. We call them igneous rock. You will have a choice bank, but that will not be in this perfect order. So you do need to practice your rock cycle diagram and get that mastered. Now remember, the rock cycle doesn't really always go in this order. It's all about the right mix of conditions. So let me put that up there. If you need to really get some more things checked there, you can pause at that point, but please study for your test. Now you have everything in one place with this review sheet. It's going to be your main study tool in addition to this video.